Chem 106, Chapter 19, Electrochemistry, Lecture 2. Voltaic cells. The energy released in a spontaneous redox reaction may be used to perform electrical work. So a voltaic or galvanic cell are devices in which electron transfer occurs via an external circuit. What it means is we can't just take a piece of one metal and dip it into the solution of other metal ions and have a reaction occur where we can get electricity from it. We have to create a circuit in a very specific way from this in order to get useful electrical work, and that's what's called a voltaic, or some people say galvanic cell. Voltaic cells are going to utilize spontaneous reactions, which gives us excess electricity, which allows us to get useful work from it if we so choose. The structure of a voltaic cell is one, and we're going to build this in lab, is one where you have two compartments. Each compartment is a half cell. In one compartment, oxidation will take place, and that's called the anode. In the other half cell, reduction will take place, and that's called the cathode. In this, a metal strip is partially immersed into a solution of that metal ion, the same metal ion. So in the case of lab, we're going to have zinc metal dipped into zinc ions and copper metal dipped into copper ions. And then we're going to connect those two by a salt bridge. So the two test tubes in which those ions exist are going to be connected by a salt bridge, which contains another ionic substance solution so that it can close the circuit by allowing cations from the salt bridge, in this case potassium, to move toward the cathode to neutralize excess negatively charged ions formed by reduction, and the anions from the salt bridge move toward the anode to neutralize the excess positively charged ions formed by the oxidation. Then each piece of metal strip is going to have an alligator clip connected to it, which is then connected to a voltmeter. And this completes the circuit around, so now electricity can flow and be measured by the voltmeter. When setting this up for a spontaneous direction, electrons flow from the anode to the cathode. So it's very important that the alligator clips be connected to the correct metal strips in order to create a spontaneous circuit. Electrons flow from anode to cathode. So the anode is negative and the cathode is positive. Electrons can't flow through solutions. Like I said, we can't just dip a piece of metal into another metal's ions and have electrons flow in a way that gets us useful work. So we're going to transport them through electrical wires that then we could harness to do work like lighting light bulbs and things like that. And so what we want to do is measure the cell potential under standard conditions. And so electrons flow from anode to cathode. The cathode has a lower electrical potential, potential energy than the anode does, and that potential difference is the difference in electrical potential, and potential difference is measured in volts, the force with which the electricity is flowing. 1 volt then is the potential difference required to impart 1 joule of energy to a charge of 1 coulomb. So a volt is a joule per coulomb. Electromotive force, EMF, is the force required to push electrons through the external circuit. So that's what we're really measuring is EMF. The cell potential, E cell, is the EMF of a cell. This is also called the cell voltage. So whenever E cell is positive, greater than 0, you have a spontaneous reaction. If E cell is less than 0, it is a non-spontaneous reaction. Standard conditions, then, for your aqueous ions are going to be 1 molar solutions. If we had gas, they would be at 1 atmosphere pressure then. The temperature of the overall system has to be 25 degrees C, which is 298 Kelvin. Under these conditions, we create what's called standard EMF, standard cell potential, or E0 cell. Remember, thermodynamically, we use that 0 to tell us we're under standard state conditions. So, speaking of standard state conditions first, let's do calculations involving the standard state first, and then we'll talk about non-standard state. So, under standard state conditions, what we measure are what are called standard reduction potentials. We don't measure oxidation potentials, we only measure reduction potentials. And that's all relative to a standard that has zero voltage. In this case, when we look at this, hydrogen ion being reduced to molecular hydrogen under, the hydrogen ions being aqueous 1 molar and the molecular hydrogen being under 1 atmosphere, that's called the standard hydrogen electrode or normal hydrogen electrode. Whenever you have it under these conditions, the voltage generated is 0. So everything is measured relative to that. So the standard reduction potentials are all written as reduction reactions. So you have some ion and you add electrons to it and you get the reduced species on the product side. And then we measure the voltage required to do so. The reactions that have an E0 reduction that are greater than 0 are spontaneous reductions relative to the standard hydrogen electrode. Reactions that have an E0 reduction that are less than 0, this should say non-spontaneous, are spontaneous oxidations. It's correct, sorry. Are spontaneous oxidations relative to the standard hydrogen electrode. The larger the difference between the reduction potentials, the larger the cell voltage that you get. And so there are tables of data. I've put at least one out into Blackboard for you that you should have when solving both lecture problems and supplemental problems. So you should have that for when we're going to solve the problems here in a minute. Okay, so when we do this, then the EMF of a cell is going to be calculated by looking at the reduction potential at the cathode minus the reduction potential at the anode. So again, this is reduction, this is oxidation. So the reduction potential of the reduction process minus the reduction potential of the oxidation process. So whenever we do this for any equation, then you're going to have to take the equation given and break it into its 2 half reactions so you know which one's the reduction half equation and which one is the oxidation half equation. The more positive the value of the reduction potential, the greater the driving force for reduction. So let's try a lecture problem under standard conditions then and calculate this. So if you look at lecture problem number 3, it says calculate the standard cell potential for the following electrochemical cell. In this we have nickel 2+ ions plus zinc metal. Right? Yes. And that's going to generate nickel metal and zinc ions. All right, so break this into 2 half reactions. The Ni2+ is going to generate Ni metal, which means again now, even though it's mass balance, we got to charge balance it. This side's 0, this is 2+, so we know we're going to have to add 2 electrons to this. For the zinc, we're going to generate Zn2+ aqueous, which means we're going to have to add electrons to this side. Now remember, when electrons are reactants, then this is the reduction half reaction. When electrons are products, this is the oxidation half reaction. So the nickel is being reduced, the zinc is being oxidized. Now, in order to use the table, everything has to be written in terms of reduction. So the nickel, I'm just going to rearrange the reactants there a little bit so that that nickel 2+ plus 2 electrons yields the nickel solid. When you consult a table, you will find that that reduction potential, that E0 red, is going to be negative 0.23 volts. Now, for this one, remember, just like a lot of other things, it's complementary. If you write it in one direction, it's oxidation, but if you write it in the opposite way, it's reduction. And since the tables are all reduction values, I'm going to turn this equation around so that I have Zn2+ aqueous plus 2 electrons is going to give me Zn solid, because that's the way I need to read this from the table, is the reduction potential from the table. And when you do, you will see this has negative 0.763 volts for it. Now, This makes sense because metals want to be oxidized. They want to lose electrons. They don't want to gain them. So we're having to force the electrons back on. So these signs are negative and it's non-spontaneous in this direction. So that makes sense. All right, so these reduction potentials then. All right, when we look at this, what we want to do to calculate the answer to the question, what is the standard cell potential? E0 cell is going to be equal to the E0 red for the reduction process minus the E0 red for the oxidation process. That then is for the reduction. Remember, the nickel is the reduction process and the zinc is the oxidation process. So we have negative 0.23 volts minus 0.763 volts. That's going to give me a raw answer of positive 0.533 volts. But now again, for final answer, because this is an addition subtraction operation, 2 decimal places, 3 decimal places, we can only have 2. So it is positive, and you got to put the positives and negatives on there. 5.3 volts. So the final answer for this question, what is the standard cell potential for this reaction? Using values you find from the table, then you will find that you end up with positive 0.53 volts from this reaction under standard conditions, which means that the nickel 2 ions and the zinc 2 ions were put into 1 molar solution. They were 1 molar solutions, and the metal pieces were put into them and the voltage measured across. All right, so we end up with 0.53 volts. Okay, so go back to the outline. Strengths of oxidizing and reducing agents. When you consider the table of standard reduction potentials and you try to make sense of what you're seeing, the more positive the reduction value, the stronger the oxidizing agent. The more negative the reduction potential, the stronger it is as a reducing agent. All right, the information can be used to predict whether one reactant can spontaneously oxidize or reduce another reactant. So relative to each other, you can look at one substance in the table relative to another, and you should be able to predict which way the reaction would go for spontaneity. All right. Cell potentials under non-standard conditions. Because remember, under standard conditions, we're working with 1 molar solutions or 1 atmosphere if it's a gas electrode. But in this course, we're sticking with solutions, aqueous solutions of ions. So standard condition was 1 molar. But what if we change the concentration? Because again, if you set up a circuit and you allow the solution to run as a battery, as it were, well, the concentration of those solutions are changing over time, and so if you let it run to the point where no ions are left, then the cell is considered to be dead. And so at that point, E equals 0 for it because there's no voltage being generated anymore. So what we can do, because, as we saw for the lecture problem we just solved, 0.53 volts, that's all fine. But what if we wanted more or even wanted less voltage out of that cell? We can change the concentration of the aqueous solutions, and that will change how much electricity you get out of it. And so this is where the Nernst equation comes into this. Nernst was a scientist that worked with all of this. And so the simplest version of this, because you'll see all kinds of versions of the Nernst equation, what I've done for the purposes of this outline is I have made it into its simplest form. The energy of the cell is going to be the standard energy cell minus 0.0592 over N, which N refers to the number of moles of electrons. Remember how when we wrote the half reactions and we had to add electrons to either the product side or the reactant side? Those are moles of electrons. And so we're going to use that in this calculation. And then we'll take the log of the oxidation concentration over the reduction concentration. And the result of all of this tells us the voltage. Remember, E0 is the standard cell voltage. And we're going to use this idea. We're going to change these concentrations as a modifier. Kind of like, remember when we did with buffer solutions? You had the pKa. And all we did then was use the concentrations of the weak acid conjugate base to modify the pKa. The same idea applies here. This is just in a different sense. This is applied to electricity. So we have the standard cell potential, and we're going to modify the concentrations to modify the overall voltage of the cell. N is the number of moles of electrons that move, and these concentrations of the oxidation solution and the reduction solution. And so we take the log of that and multiply it by 0.0592 over the number of moles of electrons. Then we subtract that overall value from the standard electron, or I'm saying the standard voltage, and that's going to give us the energy of the cell. And so a concentration cell is one whose EMF is generated solely because of a concentration difference. So we use the Nernst equation when we're talking about non-standard conditions where they are not 1 molar solutions. So let's solve the next lecture problem where we have that. Notice here, though, from lecture problem 3, we had to add 2 electrons to each side in order to make this work. So N for this is 2 because we added 2 here and 2 here. If they weren't the same and we had to, say, add 2 here and 3 here, so we had an overall of 6 to make this work, then we'd have 6 moles of electrons to transfer. But that's a little more advanced. So here, the number of electrons is, the moles is 2 because that's what we had to do to each side to make this work. But whatever number of electrons it is to make it work, that's the number of moles that's in, and that's what you would plug into the Nernst equation. All right, so remember, from this problem, we generated 0.53 volts. So we're going to go to lecture problem 4, but I'm going to leave this work here, so I'm just going to create a blank page. And we're going to look at lecture problem number 4. It says calculate the EMF at 298 Kelvin, so we're keeping the temperature standard at least, generated by this following voltaic cell. So let's say then if we had, and I'm not sure why I say that voltage is different. I think that must be a typo, and I apologize for that. Now if I've corrected it at some point here, that's fine. But when we look at this again, we have the same exact reaction plus zinc metal generates nickel solid plus zinc ions. We already calculated this under standard conditions that the E0 cell is plus 0.53 volts. So I'm gonna correct this. So if you have the lecture problems where it has a different value, disregard that. It is 0.53 volts. My apologies for the confusion on that. Okay, so, but you guys shouldn't see it. I should fix this before you ever see it. So it should say the E0 cell is 0.53 volts. All right, but it gives you new concentration that the nickel 2 plus is going to be 3 molar, and the zinc ion concentration has been lowered to 0.1 molar. So we've increased the nickel and decreased the zinc. So what we want to see is what effect does that have on the overall cell voltage. All right, and so E cell is going to be the E0 cell minus 0.0592. You have to memorize this over N times log of the oxidation process over the reduction process. And now it's really just kind of plug and chug, right? So plus 0.53 volts minus, I'm going to open this up as 0.0592 over, now remember, I left that page up for a reason, because we're talking about the same nickel zinc cell, and we determined when we wrote the half reactions that it is 2 moles of electrons that are being transferred. So that is 2 as N here times log the oxidation concentration. Remember, it's the zinc that is doing the oxidation, so that's going to be 0.100 molar over the reduction concentration, which is 3.00 molar. And those units cancel just like they should in order to do log. So plus 0.53 volts, my apologies, minus and then 0.0592 over 2 times the log, times the log. 0.1 over 3, of course, then is 0.03 to infinity. And when we do that, then we have plus 0.53 volts minus 0.0296 times negative 1.4771215. And again, it's at least close enough, right? So then equals plus 0.53 volts. Oops. It's not working so well down here. Let's try that again. 0.53 volts. And then this is negative times negative, so it's going to end up adding to it. And so we're going to add 0.043722,789. And when we do then, that's going to equal positive 0.573722789 volts, which of course we can't have all that. And so we have to decide then what the significance is. And so when we do, we had going into this calculation, we had 3 significant figures, right? And so 3 significant digits, and we take the log of it, that's going to be 3 decimal places. This has 2 and this has 3 then, so our final answer can only have 2. So the final answer to this is plus 0.57 volt. Sorry, sometimes this pen does not want to write properly. 0.57 volts. And so notice then, if you lower the concentration of the oxidation solution and either leave the reduction the same or increase it, what happens is you increase the voltage. Because again, you can see the relationship between the oxidation and the reduction and taking the log of it. The effect is lowering the oxidation or keeping it the same, and increasing or keeping it the same, whichever. You're going to modify one or both. That's going to have the effect of increasing the voltage. Had I increased the oxidation concentration and lowered the reduction, then you would have reduced the voltage. This would have remained negative, and therefore the voltage would have gone down. So it's just something to analyze in terms of what's going on here. So you should be able to calculate these both under standard and non-standard conditions. All right, let's then cancel that out, and let's go back to the outline. And so let's talk about thermodynamics again. So free energy, Gibbs free energy that you learned about in the previous chapter on thermodynamics, and redox equations. So for any electrochemical process, this whole process here, a positive E0 indicates a spontaneous process, which we like, right? And a negative E0 indicates a non-spontaneous process. That means work has to be put in order to get it to go. So we can derive an equation from all that where we involve Gibbs free energy, and that's going to be equal to negative NFE. Now N you already know as the number of moles of electrons transferred. F is the Faraday constant, named after Michael Faraday, a really brilliant scientist who did so much work in the field of electrochemistry and even the big impacts in physiology and neurotransmission. So if you have time, you really want to look up Michael Faraday and all the great things that he really contributed to science. All right, and so F is the Faraday constant, and that is equal to 1 Faraday is equal to 96,500 coulombs per mole of electron, or we could then say 96,500 joules per volt mole electron. So either way, it's 96,500 is the value you need, and then the units will hopefully cancel themselves out appropriately. Then E in there is the electromotive force of the cell. So the Gibbs free energy is minus NFE. Again, something to memorize because it won't be given to you on the exam. You have to be able to use it where necessary from your brain. All right, so observations on this then. Since N and F are positive, because it's positive 96,500 and N will always be a positive number of moles, then if delta G is less than 0, E must be greater than 0, and the reaction will be spontaneous. When the reactants and products are in their standard states, we can do delta G0, the Gibbs free energy in its standard state, if E is in E0 conditions. All right, so since delta G is related to the equilibrium constant, E0 can also be related to K. So E0, going through this definition then, where we had the delta G equals minus NFE, we can rearrange and get all this so that E0 is RT over NF ln K. But quite frankly, if you already know delta G equals minus RT ln K directly, so you don't have to go through all this necessarily. It just depends on what information you have. But E0 is RT over NF ln K. All right, so let's do a calculation for that, for delta G and equilibrium constant K then. And so we go to lecture problem 5. Calculate the standard free energy change delta G and the equilibrium constant K at 298 Kelvin for the following reaction. All right, we have then 2 iodide plus mercury 1 goes to make molecular iodine plus atomic mercury. And the E0 cell for this process is positive 0.253 volts. Okay, so what we want to calculate then is, first of all, delta G. You're asked to do both, and so do delta G first. And so we know that delta G equals minus NFE. All right, but what we need to figure out is how many moles of electrons are being moved around, because this is 0 on this side, and there's 2 minus and 2 plus there. So if you did the half reactions, then 2 iodides going to iodine, that means that 2 electrons are also moving. Hg2 2 plus to make 2Hg0, 2 electrons are moving there as well. So N is going to be 2 for this reaction, but do whatever you need in any given situation. Write the half reactions if necessary to make sure that you know how many moles of electrons. This one's pretty straightforward to see, though, that it's 2 moles of electrons that are moving. So this is going to be equal to negative 2 times the Faraday constant, 96,500, and that's but actually in this case, because we're talking about delta G, I want to modify that just a bit, because we want kilojoules for this. And we're going to use just a slightly new value for that. And so that is 96.485. So, because it's not quite 96,500, it's 96,485. But if you use 96.5, and yeah, we'll go ahead and do that. I apologize. I won't make you memorize the more strict one. So let's just say it is 96.5 kilojoules, because again, it was 96,500 joules, but because we're talking about delta G, we want kilojoules per coulomb mole of electrons, right? Or yeah, I'm sorry, we're per mole volt. All right, times E, which was positive 0.253 volts. So volts cancels, and this is moles, so moles cancels, leaving us just with kilojoules, which is great. And now your value is going to be a little different because I use 96.485 and this is 0.5, but with any luck, it's going to work out the same. And so when we do this, then I ended up with negative 48.82141 kilojoules. Now again, because I used 96.485, which shouldn't be that much different than 96.5, but if yours is different a little bit, that's okay. But so then for me, because in terms of significant digits, we have to go by the E cell. That's the measured number. This is constant and this is infinitely precise, so we go by the E cell voltage. That's 3, and so cut it there. So delta G then is negative 48.8, not volts, kilojoules. Okay, so now using that, we can calculate K, because if we know that delta G equals minus RT ln K, that K equals e to the minus delta G over RT, right? And so let's break this out so that we have delta G over RT. And so that's going to be the negative 48.8 kilojoules over R, which again is going to be 0.008314 kilojoules per mole K. Remember that from earlier, times 298 K. The K's cancel out, and the kilojoules cancel out. And technically delta G is already still, even though it cancels out up here, it's still per mole, so those cancel out also. So that means it's dimensionless, so we can do the e to the minus. All right, so when we do this, then the raw answer there is going to be minus 48.8 over this denominator, which is 2.477572, and that's going to give us negative 19.696703.06, and so, oops, not what I want there. K equals e to the minus 19.696. I always keep track of charge, right? Signs. 696.703.06. And that's going to give you a value of, at least, in mine, because of how we did all this, I got 3.5823.618.54 times 10 to the 8th. And remember, there's no units here. Now, when it comes down to all of this, then the number that was the only one, because R and T are constants, our temperature doesn't count. R is constant, T doesn't count. So the delta G is the only one that matters. And so when I did this, I had 3 significant digits in this division, so I got 3 significant digits here, which means I have 1 decimal place. The reverse log of anything, however many decimal places, that becomes total number of significant digits, so only 1. So this must be 4 times 10 to the 8th as the final answer for this problem. All right, back to the chapter outline. I've written a lot more to this outline for you, but quite honestly, this is where the testable material ends. I have added material on batteries and fuel cells for you to read if you want, if you're more interested on how things work in terms of, like, say, the lead acid batteries versus the alkaline batteries versus the NiCads and lithium ions, nickel metal hydrides, and hydrogen fuel cells. I've written more information for you in case you're interested. And then I've also added a section on corrosion, what it means, and how we can engineering-wise help prevent corrosion through galvanic intervention. Okay? And then finally, the last section on electrolysis, what that means and how that works. But these sections are not on your exam, but they are there for you to hopefully read and find interesting. And if you want to discuss outside of class, which means come visit me in my office or send me emails. But sections 7, 8, and 9 are not on the exam. Your information really stops with calculating delta G and K. This concludes Lecture 2.